Thanks, Heiner. Good morning. Welcome everybody to my talk entitled Combining Phenotyping and Crop Growth Modeling. In my talk, I will focus on the work that has been done by my group in the last month. I will focus on near future plans and also on cooperations and joint work. But let me first start with a short introduction. Agriculture is facing several challenges, including the increasing demand for food, fodder, and fiber, the climate change, loss of biodiversity, and negative impacts of agriculture on ecosystem services and on the environment. The FAO proposes that a so-called sustainable intensification is the most promising path. Frank already explained that quite nicely in his talk. To keep it short, the main idea is to increase crop production while increasing or at least stabilizing biodiversity and resource use efficiency. We need multifunctional cropping systems that not only provide food, but also are habitat for animals and provide ecosystem services. So now the question is, how can this be achieved and what are the effects of certain measures, such as of decreasing fertilization or of increasing biodiversity and ecosystem services? In our group, we use feed data together with process-based one-dimensional feed-scale crop models to prove this understanding of the systems of the agroecosystems. Let me explain this shortly in that slide. So some of us, we conduct experiments and even more also collect data on these experiments with the main aim to better understand certain processes or the system. And this data can then be used within a model with different methods and different objectives. So the data can be used, for instance, to set up and calibrate and validate the model, and then, for instance, for regionalization. Let me give you an example. For instance, one could conduct a nitrogen fertilizer experiment and use the data for model calibration and validation, and then estimate the effect of different nitrogen application management strategies on a regional scale to get an idea on the change of yield and losses. Another way we can use models is to test hypotheses. We can include certain or implement certain hypotheses into the model in form of equations. For instance, the relationship of or the effect of biopores on root length elongation, and this can be then we can then use experimental data to test and to validate this hypothesis. The data can also be used for data assimilation. This is an example here on the bottom of a colleague of us. You can see LAI over time, and in gray, these are ensemble runs of a model, so multiple runs of a model, and in orange, the ensemble mean, and red crosses are the observations, so the real data is used to force the model, or let's say to prove the model predictions. We can use the model for regionalization, for testing our hypotheses, and we can also use it for generalization. Let's say we conduct a feed experiment with 15 different sowing densities. We can then prove and validate our model on that data, and then can use it for generalization and test an infinite number of sowing densities. Here is a definition of colleagues. What are one-dimensional feed-scale models? These models are dynamic computational tools that simulate the development and growth of crops in relation to environmental conditions and to management practices. On the bottom, you can see a table that lists the processes that are commonly simulated in this type of models. They commonly simulate phenology, then crop growth, so the root growth, shoot growth, and of course yield. Then evapotranspiration, water uptake, and nutrient uptake. Most models consider nitrogen, several consider phosphorus and potassium, and few ones also consider other nutrients. And many models also consider stresses such as water deficit or excess of water, excess of water, and then also nutrient deficiencies and low or high temperature stresses. I'd like to give you just one short example on how daily biomass accumulation is quite often simulated. So the potential daily biomass accumulation is calculated by multiplying the crop-specific light use efficiency with the intercepted photosynthetic active radiation. And the latter depends on incoming radiation, which comes from the weather data, then a crop-specific constant, the extinction coefficient, and the actual LRI, which changes over time. So this is the way how the potential daily increase of biomass is calculated. And if stresses occur, we can also consider that. Most models consider drought stress. There is not enough water available to meet the transpiration demand, nutrient stress, temperature stress, and the stresses are not additive, but the major stress that occurs at a certain day then finally reduces the potential biomass increase. So at the end of the day, we have calculated a certain biomass production, and this amount is then partitioned into the different crop organs, into the root and the storage organ and the leaf and stem. And this partitioning depends on crop-specific partitioning tables that also change over time. With this, I would like to come to the main part of the talk. I took this scheme from a document Heiner circulated once. It shows the technologies and tools and aims of Phenorob. And the red borders show which topics myself and my group are addressing. The broader the border, the more we address it. And who is we? Myself, I am junior research group leader in CP5, and I'm in the group of Frank Ewert since 2016. And last summer, I employed 3 PhD students, Derecha, who focuses on light distribution and water dynamics in crop mixtures. And Sophia, she focuses on root growth and end dynamics in crop mixtures, but also in crop rotations with cover crops. And then there's Gina Lopez, she's part of CP3. She's a shared PhD student with Andrea Schnepp and Frank Ewert. And Thomas Geiser, she focuses on root phenotyping and model prediction of root and shoot growth. With this, I would like to start now with the first CP5, CP5.1 actually, which focuses on mixed cropping. And here our task is to improve the crop models and the crop model prediction, and also to support organic farming. I'm sure almost all of you are aware of the 2 huge mixture or intercropping tries where Thomas Döring is responsible for them, and he has a PhD student, Maduri. She does a lot of work on those tries. There are 2 of them, one at Campus Altendorf and one at the organic farm Wiesengut. And they are, as I said, huge. Each of them consists of 320 plots. We grow 2 farmer bean varieties and 10 wheat varieties, and there are also 2 levels of sowing densities. And a lot of people, like Julie, for instance, or Daniel, they use different kinds of sensors and digital technologies on those sites. In general, we can say that there is a large variation in intercropping performance, which can be read in literature, and there's definitely a need for optimization. We have to find out which are the key factors and the key traits that lead to high positive mixture effects. So I don't want to go so much into detail of the trial, just to give you a very rough idea on the first outcomes of last year. In general, there was a positive grain yield effect of mixing farmer bean and spring wheat. This is calculated by using the index land equivalent ratio. The effect of genotypes and sites was larger than the one of the sowing densities, and a taller fava bean variety competed better than a smaller one. In that trial, as I said, we tested 10 different spring wheat varieties, and they are similar in maturity, but they are different in plant height. So this was one of the focus traits in that trial, or in that variety selection, the plant height. To give you an idea on the range of the maximum plant height, around flowering springweed plant height ranged from 57 to 67 centimeters, and plant height in faba bean was quite similar. The taller variety reached 62 centimeters and the smaller one 57 centimeters. And as you can see here on the bottom, there is a weak correlation between plant height and grain yield. So the higher the beans are, the taller the bean plants are, the higher the bean grain yield, the final grain yield, but also the lower the wheat grain yield. So there is definitely a competition for light. But as you can see, it's it's not really a strong correlation, and there seems to be other factors that influence the absolute grain yields in the mixture. So if we correlate, for instance, the total intercepted light around flowering with the final yield, we also find a positive correlation. The higher the intercepted light, the higher the yield. This is true for both crops. But also, if we correlate, for instance, soil water content with yield, we find some weak correlations. For instance, one example here is the soil water content at 30 centimeter soil depth at end of May, correlated with with wheat grain yield, and the lower the soil water content, the higher the yield was at the end, because most probably the crops here already took up a lot of water and already had high biomass. There's a very weak correlation also for deeper soil water contents. My intention was not to impress you somehow with fancy results. What I wanted to show you here is that there are complex interactions and large variations, so it's not clear which is the main factor that influences how high the yields are. It's not only the height, plant height, it's not only the water uptake or whatever, it's a combination. We want to use crop models to disentangle these influencing factors. We are now at the very beginning of doing that, so I will show only very preliminary results. First, let me very briefly explain you the main concept of this intercropping or mixture component in our simplex model. So in the field, we have an in-row mixture. That means within each row there are wheat and bean plants next to each other. But we assume that they are not within mixture, but a row by row mixture in the model. And we still use a one-dimensional model, but we run the crop components twice. So we have one. The environmental components are run only once, but the crop components run twice in the model. So how do we consider the competition? The above ground competition, here the share of incoming radiation depends on the proportion or the coverage of both crops on the field, and also on the difference between the plant heights. And below ground, the ratio of root length density per crop and soil layer determines the splitting of plant water uptake. So let's say that the root length density of crop A is 3 in that layer and it's 1 in that layer. That means that crop 1 takes up or can take up 3 times more water than crop 2, sorry. So this is an example with which I want to show you what's the aim of this modeling exercise. It shows the grain yield of both crops for different faba bean plant heights and spring wheat plant heights. So the z-axis is the grain yield, and these axes are the maximum plant heights, here faba bean and here spring wheat. And this is here the yield of spring wheat and this one of faba bean. So at that point, when the faba bean plants are very short and the spring wheat plants are very high, faba bean yield is very low and spring wheat yield is very high. And at the other corner, if the spring wheat plants are very short and the faba bean plants are very tall, the spring wheat yield is low and faba bean yield is high. If you combine both curves, we get that curve, which shows the total grain yield of both crops. It's just the sum of both. And we can see here that the maximum yield is obtained if we combine rather short wheat plants with tall fava bean plants. So the fava bean determines actually the total yield. Now let me give a short outlook on CP51. We are now in the process of improving and calibrating this intercropping model. We are now in the process, but we also want to continue and further use further data with the model to test and improve the predictions. The main aim is to find optimal plant traits, feed design and management. And this year we will, Sophia will focus on root growth, so we will also have a deeper look into the competition below ground. With this, I would like to come to the second topic, which can be not really assigned to a CEP, but I'm sure you already heard about it, so I don't want to go so much into detail. It's the phenotyping campaign at the long-term fertilizer trial DECOPSO, which is a nutrient fertilizer trial. And we started in 2019 together with Lasse and Diana to combine high-intensive ground truthing with regular drone flights. And on the left side, you can see a list of the variables we are measuring. But for me personally, the most interesting part are the roots. And last year we had the first publication resulting out of this campaign here at the bottom from Sophia. One short, let me show you a few first results on the winter wheat data from last year. On the bottom left, the panel shows the shoot biomass over time for 5 sampling dates, and the different bars are different treatments. So gray, for instance, is the treatment that receives the highest amount of fertilizer. The cyan one is the one that receives no nitrogen, and this is the one that receives no fertilization at all. And in my opinion, this trial is quite nice, quite interesting for the pilots, because with one flight they cover a very wide range of values. So not only of biomass, but also of leaf area index and height. For me personally, more interesting is that graph, which shows the root length density over depth for the 7 different treatments, and it shows that the root length density at the topsoil was highest in the treatment that receives full fertilization, and the treatments that received no nitrogen and the one that were not lined. Whereas the root length density is rather low in the treatments that received no fertilization or no phosphorus and no potassium. So what are the objectives of that campaign? We want to generate basic knowledge on root growth under nutrient deficiency on a feed scale. It's amazing. There's really a huge lack of information. We are now writing a review paper. It's really very hard to find any literature on, or to find literature on that topic on feed scale. We want to use the data because it's for improvement of model predictions, because it's very comprehensive. It includes, for instance, root biomass, which is quite often not observed. And there are several cooperations ongoing. The first one I've already mentioned. We provide ground truthing data for several people. We offered, or we already transferred the data to the 3D modelers, to Guillaume and Thomas, for their 3D wheat model. And then there are 2 other initiatives I will focus on in the next slides: the non-invasive diagnosis of nutrient deficiencies and the data challenge. So with this, I'd like to come to the next topic, non-invasive diagnosis of deficiencies, which is on phenotyping, machine learning, and informed management. Last year, we published a publication together with Jürgen Gall and his PhD student Yin Hui and Gabriel Schaaf and some others, entitled Deep Learning for Non-Invasive Diagnosis of Nutrient Deficiencies in Sugar Beet using RGB images. In that year, in 2019, we took thousands of images with a camera and we labeled them. Each image had a label like no N or no P, or unfertilized or fully fertilized. And we then split the data into two parts, training set and test set, and then he used it to identify, to find out if he can use that algorithms for detection of mutant deficiencies. And one outcome I would like to highlight here, because I think it's quite important for PhenoRock, is that the recognizing mutant deficiencies across crop development stages remains an open problem. So when Yinghui, for instance, used images from July and trained the model on these images, and then tested the model on images from, let's say, from November, the model performed rather or not so well. So the transferability was not very well. Now let me come to the data challenge. There are, I'm not sure, 2, 3, or 4 data challenges planned, and this is one of them. It's on a quite similar topic on non-invasive detection of mutant deficiencies in wheat. We will use drone data from Jan Weiler. He flew on that site last year quite frequently, every 2 weeks. We will use this data set for training, and we will label the images similar to the task, to that paper I presented before. And the test data will then come from this year, because we then grow there the same variety. And the next level of this data challenge could be that we run the algorithms trained on winter wheat on another series, such as winter rye, which is also cultivated on that site in this year. With this, I would like to come to CPU3, which is on improved crop predictions, a crop model and predictions on root phenotyping and on mobile sensing. We conduct 2 quite similar experiments on 2 sites. One of them is on the rhizoclone facility in Sennhausen, and the other one is part of the central field experiments at Campus Altendorf. We have the same treatments. We combine, it's a variety mixture treatment. We combine 2 different varieties. Last year it was maize, and this year it's winter wheat. And we combine a shallow rooting and a deep rooting crop. And both sides have their advantages and disadvantages. So the advantage of the rhizoclone facility is the rhizoclone facility, and the disadvantage of the advantage of Campus Altendorf is that the size of the field is much bigger, and we have replicates which we don't have in Sennhausen. We conduct there a lot of shoot measurements, and together with Lutz Weiermüller and Niklas Brüggemann, they both also focused here on nutrient dynamics. And what is very important for us this year, that we work together with Valentin and Andreas Kemner. They installed their site system. I'll say a few words on that in a few slides. It's an invasive method. No, it's a non-invasive method to sense roots in the field. And here in this slide, I'd like to say a few words on the rhizoclone facility in Sennhausen. It consists of 2 main feeds. You can see them here and there, and the distance is about 100 meters, but the soils differ very much. So here the stone content is about 50%, and here it's, I don't know, maybe 1%. And in this feed there are 2 cellars, which are here below, and you can go downstairs, and then you can, or the colleagues in Forschungszentrum Jülich, they conduct a lot of measurements there. Here, for instance, they use the mini rhizotron system to observe roots, and they also use ground penetrating radar system to measure 3D soil moisture. And also here we have this site system in one of these fields. And the aim of us, or of GINA, is to forecast root and shoot growth with a focus on root growth, because here we have a very intensive measurement of root growth over time. as I was talking about the site system, I'll just very shortly explain you what it is. But I guess most of you know that. So Andreas Kemner and Valentin, they measure the root distribution and activity, and it's a non-invasive measurement, and the system is spectral electrical impedance tomography, and we provide them the verification. So my group, we do the coring to verify this data, and to analyze the images, we use the machine learning software Root Painter. With this, I would like to come to the last topic, or biodiversity, which is on machine learning, but also on reduced agrochemical usage. We want to use acoustic signals as a proxy for biodiversity. Maybe some of you have this app on your mobile phone where you can record birds, and then you see the spectrogram with the pattern of the sound. And this app then identifies the birds according to this pattern. And we want to do something very similar, but we want to do it with bees or with insects, flower visitors that make sound, bees, bumblebees, and so on. And for this, we want to use microphones, and we have done some free experiments, as you can see here at the bottom. But this year, we want to start, we will have a real trial with maize and Phacelia. Phacelia is always visited quite frequently by bees. And we want to verify this with catching insects and also taking videos of the insects. With this, I'm at the end of my talk with a summary and outlook. As you have seen, we've collected first phenotyping data quite often together with colleagues. We want to use observations, some data we're already using, but we also want to use further data to improve our model predictions. In CP3, the focus is on the use of sensed root data in the model. And in CP5, the focus is on the model-based finding of optimal traits, feed design, and management. With this, as you know, I'm always open for cooperations and synergies. So if you have something in mind,